Welcome to this video lecture on petroleum refining. My name is Dr. Jinish. I am from Department of Chemistry, Ramaya University of Applied Sciences. In this video lecture, mainly 4 points will be discussed. First point, what is petroleum or crude oil and how petroleum is formed on earth. Second point is the significance of petroleum. Third point is the composition of petroleum. Last point is the separation of useful components from petroleum using fractional distillation. Petroleum is a naturally occurring yellowish black liquid found in geological formations beneath the Earth's surface. Petroleum is a fossil fuel. Fossil fuel is a term used to describe a group of energy sources that formed from ancient plants and organisms during the Carboniferous period approximately 360 to 286 million years ago, even before the age of dinosaurs. At that time, the land was covered with swamps filled with organisms and plants. As they died, they stayed at the bottom of the swamps and the ocean, and over millions of years started decomposing under layers of sand, clay, and other minerals. Different types of fossil fuels formed depending on the combination of organic matter, temperature, time, and pressure conditions while decomposing. There are 3 types of major fossil fuels: coal, oil, and natural gas. Coal is formed from the ferns, plants, and trees which hardened due to pressure and heat. Oil was formed from small organisms like zooplankton and algae, where pressure caused the more complex organic matter to decompose. Natural gas was formed by the same process as oil but was only exposed to more pressure and heat, causing to further decompose and turn into gaseous form. At the molecular level, oil and gas are the hydrocarbons made up of hydrogen and carbon atoms. The constant pressure and movement of the Earth's crust squeezes the oil and gas through the pores or spaces within the rocks. Some oil and gas reaches the Earth's surface and seeps out naturally into land or water. Often, it is trapped beneath the surface by impermeable layers of rock structures like rock faults. Within the crust, oil or gas deposits build up and form reservoirs. Reservoirs are like vast sponges filled with oil and gas. They can be as large as a city. To find oil and gas deposits, geologists use a number of different survey techniques, including seismic surveys, gravitational surveys, and geological mapping. Seismic surveys use reflected sound waves to produce a 3-dimensional view of the Earth's interior. New technologies such as 4-dimensional projections and sophisticated graphic renderings of rock structures are improving the way we find conventional oil and gas deposits. Energy resources that are currently difficult or expensive to extract are called unconventional oil and gas. Oil has become the most important source of energy since the mid-1950s and became the lifeblood of the industrialized nations. Its products underpin modern society, mainly supplying energy to power industry, heat homes, and provide fuel for vehicles and aeroplanes to carry goods and people all over the world. In addition, it also benefits our lives in being vital to the production of many everyday essentials. Oil's refined products are used to manufacture almost all chemical products, such as plastics, fertilizers, detergents, paints, and even medicines, plus a whole host of other products that you might not expect. Petroleum is the raw material for fuels such as petroleum gas, gasoline or petrol, naphtha, kerosene, diesel, fuel oil or heavy oils. Petroleum is also used to make useful petrochemicals such as benzene, toluene, other organic solvents, fertilizers, adhesives, pesticides, plastics, bitumen, petroleum wax, lubricating oil, etc. Now we will see the composition of petroleum. By elemental composition, the weight percentage of different elements present in petroleum is given in this table. Carbon 83 to 85%, hydrogen 10 to 14%, nitrogen 0.1 to 2%, oxygen 0.05 to 1.5%, sulfur 0.05 to 6%, and metals less than 0.1%. Now the type of compounds present in petroleum. Based on the type of compounds, the composition by weight of these compounds are given in this table. Alkanes, they present mainly from 15 to 60%, average 30%. Naphthalene ranges from 30 to 60%, average 49%. Aromatics ranges from 3 to 30%, average 15%, and the remaining asphaltics. What is petroleum refining? As such, petroleum cannot be used as a fuel. By the fractional distillation of petroleum, we can get useful products such as refinery gas, gasoline, naphtha, kerosene, diesel oil, lubricating oil, fuel oil, greases, and wax and bitumen. And you can see all these useful compounds, they differ in the number of carbon atoms present in their compounds. For example, refinery gas mainly contains the hydrocarbons with 3 or 4 carbon atoms. Gasoline, it is a mixture of hydrocarbons where the number of carbon atoms in the hydrocarbon chains ranges from 7 to 9. For naphtha, it is 6 to 11. Kerosene, it is 11 to 18. Diesel oil, 11 to 18. Lubricating oil, 18 to 25. Fuel oil, 20 to 27. Greases, 25 to 30. Bitumen, above 35. Now you can see the boiling point of these compounds, they also differ, and we can see if more number of carbon atoms are present in the hydrocarbons of these mixtures, the boiling point also increases. For example, refinery gas contains hardly 3 or 4 carbon atoms and their boiling point is below 30 degrees Celsius. Diesel oil contains 11 to 18 carbon atoms and the boiling point is 200 to 300. For fuel oil, the number of carbon atoms 20 to 27 and boiling point 350 to 450 degrees Celsius. Actually, this property, that means the number of carbon atom increases, boiling point increases. This property we can use to do fractional distillation of petroleum to get these useful products. To simplify the petroleum distillation process, we consider one distillation tower in which distillation process taking place. Crude oil is supplied to a furnace before adding it into the distillation tower where crude oil is heated. The heated mixture is fed into the bottom section of the distillation tower. This bottom section is the hottest point in the distillation tower where the temperature can reach as high as 400 degrees Celsius. Components which are not vaporizable at this temperature becomes the lower bottom products. Components in vapor form rise up to the tower through a different series of distillation stages. The temperature decreases as the vapors rise through the tower and the components condense. The products getting from each distillation zones are known as product streams. Products from the distillation ranges from gases at the top to very high viscous liquids at the bottom. In all cases, these product streams are considered as unfinished products and further processing is required to make it useful products. Light products separated at the top contains propane, butane and isobutene. This stream is also known as petroleum gas and it can be liquefied to produce liquefied petroleum gas or LPG. Gasoline stream used as a good fuel for automobiles. Naphtha stream can be utilized to convert gasoline by reforming process. We will discuss reforming process in the next video. Kerosene can be treated to obtain jet fuels. Heavier oils such as fuel oil can be converted into useful fuels by cracking techniques. We will study about cracking techniques in the next video. The process depends on the quality of the petroleum as well as market demands. The lower products, asphalt or bitumen, are used for construction process. Now we will summarize the petroleum distillation process. Crude oil from the field is a mix of hydrocarbons of different molecular length. By fractional distillation, the components in the crude oil can be separated, and this process is known as petroleum distillation. During this process, low molecular weight hydrocarbons will be separated first due to their low boiling points, and the higher molecular weight hydrocarbon mixtures separate later. Very high molecular weight hydrocarbon mixtures will be at the bottom of the distillation column. Now we will summarize the video. In this video, the following questions were answered. How crude oil was formed on Earth's crust? What is the significance of petroleum in the present scenario? What is the composition of petroleum? What is the principle behind the separation of useful products from petroleum? Explain the petroleum distillation process. What are the products obtained from distillation of petroleum? Thank you for watching the video. Good morning students, Jinish here. Today we will study cracking in petroleum processing. In this video lecture, we will study about the definition of cracking, significance of cracking, and types of cracking. From the last video, we studied about the fractional distillation process of petroleum to obtain useful products. The major products in the fractional distillation column are refinery gas, which is also known as petroleum gas, which contains 3 to 4 carbon atoms in their hydrocarbon chains. Petrol, it contains 7 to 9 carbon atoms in their hydrocarbon chains. Kerosene, 11 to 18 carbon atoms. Naphtha, 6 to 11 carbon atoms. Diesel, 11 to 18 carbon atoms. Fuel oil, 20 to 27 carbon atoms. Lubricating oil, 18 to 25 carbon atoms. Waxes, 25 to 30 carbon atoms. Bitumen, above 35 carbon atoms. The products separated during the fractional distillation process was based on their difference in boiling point. Lower molecular weight hydrocarbon based products, which will separate at a lower temperature, for example refinery gas, petrol, etc. Higher molecular weight hydrocarbon based products are separated at higher temperatures, example fuel oil, lubricating oil, etc. Very high molecular weight hydrocarbon based products will be at the bottom of the distillation column, and they won't vaporized in the column. For example, waxes, bitumen, etc. Among these fractional distillation products, which products are more useful? Widely used and more useful products are low molecular weight hydrocarbon based fuels, example refinery gas, petrol, etc. Higher molecular weight hydrocarbon based products such as fuel oil does not have much commercial value. Higher molecular weight oils are also known as heavy oils. Can we convert these less useful heavy oils into useful products? Yes, and that method is known as cracking of fuel. So the definition of cracking is this. Cracking is the breaking down of molecules with longer hydrocarbon chains into molecules with shorter hydrocarbon chains. This process you can achieve with the help of heat as well as
stacks of trays. The liquid is easily collected and separated by weight. The lighter and medium weight liquids require less processing before they're ready to be used in cars and trucks. The heavier liquids need more processing to become useful. A process called cracking is used to maximize the usefulness of heavy oil. Heavy oil has long strings of carbon and hydrogen molecules. Using a catalyst, these molecules can be broken into smaller chains, transforming the heavy oil into lighter, more valuable fluids.
We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small-chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long-chain molecules. The process of cracking breaks down long-chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short-chain hydrocarbons to meet the demand for them, as the longer-chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out.
Types of cracking. Cracking can be done with the help of heat, and that type of cracking is known as thermal cracking. And thermal cracking can be done in two different ways: liquid phase cracking and vapor phase cracking. Cracking can also be done with the help of a catalyst, which is known as catalytic cracking. Catalytic cracking can also be done in two different ways: fixed bed catalytic cracking and fluidized bed catalytic cracking. So cracking can be done in two different ways: thermal cracking and catalytic cracking.
Carbons. There are two methods of cracking in use, such as thermal cracking and catalytic cracking. Thermal cracking. Cracking that is carried out by the application of heat and pressure is known as thermal cracking. Here, the bigger hydrocarbon molecules break down to give smaller molecules of alkanes, alkenes, and some hydrogen. This process may be carried out either in liquid phase or vapor phase. Liquid phase thermal cracking. The heavy oil is cracked at a temperature of 475 to 530 degrees Celsius and pressure of about 100 kilograms per square centimeter. The cracked products are then separated in a fractioning column. Vapor phase thermal cracking. This type of cracking is suitable for oils which may be readily vaporized. The crude oil is first vaporized and then cracked at about 600 to 650 degrees Celsius under a low pressure of 10 to 20 kilograms per centimeter square.
Thermal cracking can be done in two ways: liquid phase thermal cracking and vapor phase thermal cracking. In liquid phase thermal cracking, heavy oil is pumped into the coil, kept at 420 to 550 degrees Celsius under a pressure of 15 to 100 kilogram per centimeter square. Here the pressure is quite high. Good quality of gasoline is produced at this temperature. Gasoline with low octane value around 60 to 70 is obtained, which can be mixed with a higher octane value gasoline and then be used in automobile. What is octane number? That we will study in the next video. Vapor phase thermal cracking. Here the heavy oil is heated in a heater at 400 degrees Celsius to convert it into the vapors. Then these vapors are passed into the reaction chamber, which is maintained at a temperature of 600 to 650 degrees Celsius under the pressure of 10 to 20 kilogram per centimeter square. Here you see the pressure is lesser than that of liquid phase thermal cracking. And the kind of petrol that we get is of high quality in vapor phase thermal cracking, where you can get an octane number up to 75 to 80. Catalytic cracking can be done in two ways: fixed bed and fluidized bed. In fixed bed catalytic cracking, you can see a catalyst chamber where there are beds where we have to put the catalyst. This catalyst will be fixed in that bed, and we have to pass the heated heavy oil. How can we heat it? With the help of an electric heater. Just heat it, and that heated oil should be passed to the catalyst chamber, where the catalyst molecules will be in touch, or they will be colliding with the heavy oil molecules, and the heavy oil molecules will be converted into lower molecular weight hydrocarbons, and those hydrocarbons we can separate it using a fractional distillation column, a small fractional distillation column. So we will get lower molecular weight hydrocarbons. So in fixed bed catalytic cracking, vapors of the heavy oil are heated in the presence of catalyst, due to which a better yield of petrol is obtained. Heavy oil is vaporized by heating in electric heater, and vapors are passed over a series of trays containing the catalyst, and generally using catalyst aluminum silicate, bentonite, bauxite, zeolite. And the reaction temperature will be somewhere around 425 to 540 degrees Celsius and a pressure of 1.5 kilogram per centimeter square. In fluidized bed catalytic cracking, you can see a reaction chamber where catalyst will be suspended or moving with the help of an inert gas. So during this movement, heavy oil molecules will be in collision with the catalyst particles, and the number of collision will be very high because of the movement of the catalyst. So the heavy oil molecules will be converted or will be splitted into lower molecular weight hydrocarbons. These lower molecular weight hydrocarbons you can separate using a small fractional distillation column, where you can get lower molecular weight hydrocarbons separately. So in the fluidized bed catalytic cracking, we have to supply heavy oil fraction, and the catalyst generally we use aluminum oxide and silicon dioxide. They should be in finely powdered form. Temperature should be 550 degrees Celsius. Pressure 1 to 2 atmosphere. Time only 3 to 4 seconds. So for this process, the time required is only 3 to 4 seconds. That's why this fluidized bed catalytic cracking is now presently widely used in industries, mainly in the refineries. The production yield around 70%. So in this video we learned what is cracking, why it is necessary in petroleum industry, types of cracking and their characteristics. Welcome to the video lecture on reforming process, knocking in engines, octane number and cetane number of fuels. My name is Dr. Jinesh from Department of Chemistry, Ramaya University of Applied Sciences. In this video lecture, 7 points will be discussed. 1. Quality of petrol in terms of octane number, improvement in octane number, reforming process, knocking in petroleum engine, octane number of petrol, anti-knocking agents, cetane number of diesel. In the previous video lectures, we studied that petrol or gasoline is derived from crude oil by the fractional distillation process. Also, we studied that the distillation products need further processing to use as finished fuel products. Quality of the fuel products depends on the source and quality of crude oil, fractional distillation process, and the post-fractional distillation processes that we do after fractional distillation. Quality of gasoline or petrol is mainly determined by its octane number. We will study about octane number and its definition by the end of this video lecture. If the gasoline has higher octane number, then the gasoline will create less knocking in the engines. If the gasoline has lower octane number, then the gasoline will create large knocking in the engines. We will also study about knocking by the end of this video lecture. Petrol is a mixture of hydrocarbons where the number of carbon atoms in the hydrocarbon chains ranges from 4 to 12, but majority of the chains will have 7 to 10 carbon atoms. The hydrocarbons present in petrol are paraffins, alkanes, olefins, alkanes, and cycloalkanes, cycloalkenes, aromatic compounds, etc. Among these hydrocarbons, some compounds will be linear, some will be branched, some will be cyclic and aromatic. If the hydrocarbons in the petrol are majorly branched, cyclic and aromatic, then the octane number of petrol will be high. If the hydrocarbons in the petrol are straight linear chains, then the octane number of petrol will be low. A significant amount of petroleum products such as naphtha contains mainly straight chain hydrocarbons. Similarly, the petrol used to obtain from petroleum also contains a significant amount of straight chain hydrocarbons. Straight chain hydrocarbons leads to lower octane number and more knocking. Knocking is a rattling sound in engines. How to increase the octane number? How to decrease the knocking in petrol engines? If we can convert these linear straight hydrocarbons into branched or cyclic hydrocarbons, octane number of the petrol will be increased, and this process is known as reforming process. Definition of reforming is conversion of straight chain hydrocarbons into branched chain, cyclic and aromatic hydrocarbons, resulting in upgradation of petrol, that is improvement in octane number, is known as reforming. If the reforming is done in the presence of a catalyst, then the reforming is known as catalytic reforming. For example, linear hexane into cyclohexane. Mainly 4 types of catalytic cracking processes are being used: isomerization reaction, hydrocracking, dehydrogenation reaction, dehydrocyclization reaction. First case, isomerization reaction for reforming. In this given example, the straight chain hydrocarbon, that is N-hexane, in the mixtures of hydrocarbons converted into its branched isomers such as 2-methylpentane and 2,3-dimethyl-butane. These 3 compounds are isomers as they have the formula of C6H14, and the only difference is in their number of carbon atoms in their long carbon chains. N-hexane has 6, 2-methylpentane has 5, and 2,2-dimethyl-butane has 4 carbon atoms in their long carbon chain. So they are chain isomers as they have difference only in the number of carbon atoms in the longer chains. So in this case, linear and straight hydrocarbon is converted into branched hydrocarbons, thus the octane number improves. This can be achieved with the help of heat and catalyst. Second, hydrocracking reforming. In hydrocracking reforming, in the presence of hydrogen, the straight chain hydrocarbons will be splitted into smaller hydrocarbons. The word hydrocracking came because of the usage of hydrogen for cracking the longer linear hydrocarbons into shorter hydrocarbons. For example, normal heptane with the help of hydrogen is cracked into smaller hydrocarbons such as propane and butane. Similarly, decane is cracked with the help of hydrogen to produce 2 smaller hydrocarbons of pentane. Third technique, dehydrogenation reaction reforming. In this process, cyclic hydrocarbons will remove hydrogen from their structures and becomes aromatic hydrocarbons which have much higher octane number than cyclic hydrocarbons. Here you see a cyclic hydrocarbon removed 3 hydrogen molecule from its structure and became an aromatic hydrocarbon. So by doing this process, the octane number of the fuel will be increased. The fourth technique, dehydrocyclization reforming process. Straight chain hydrocarbons undergo cyclization followed by dehydrogenation to produce aromatic hydrocarbons. So here 2 processes will be happening. One is dehydrogenation, that means hydrogen will be removed. At the same time, cyclization also will happen, and the product will be an aromatic hydrocarbons. Normally aromatic hydrocarbons possess higher octane number. Here you can see the straight chain normal octane is converted into aromatic ethyl benzene, which has higher octane number by the removal of hydrogen molecules. Now we can conclude the reforming process. Reforming process is essential to produce high quality, high octane number petrol from the naphtha stream and low quality gasoline that we obtained from the fractional distillation of crude oil. By converting the straight chain hydrocarbons into branched, cyclic and aromatic hydrocarbons, octane number of fuel will be improved. If there is something everyone can agree on, it's that the cars can make weird noises. It could be a squeal, a clunk, or even a rumble and roar. If the sound is closer to a knock, you may be dealing with problems under the hood. Problems that could cause engine damage if left unresolved. We know that the combustion of fuel in engine generates energy for the vehicle. Fuel-air mixture will be compressed and undergo combustion and produce energy. However, at high compression ratios, depending on the composition of the fuel, premature combustion of part of compressed air fuel mixture in the cylinder producing intense high frequency pressure waves. These pressure waves force parts of the engine to vibrate, which produces an audible knock. Knocking may be defined as the production of a shock wave in an IC engine as a result of an explosive combustion of fuel-air mixture leading to a rattling sound. Knocking is caused by premature combustion of part of the compressed air fuel mixture in the cylinder. Knocking is mainly due to the faulty spark of the engine, low octane fuel, carbon deposits in the engine. Knocking can cause overheating of the spark plug points, erosion of the combustion chamber surface, and rough combustion chamber surface and inefficient operation. It can be avoided by adjusting certain variables of engine design and operation, such as compression ratio and burning time. But the most common method is to burn the gasoline of higher octane number. When gasoline engine became more powerful in 1920s, it was discovered that some fuels knocked more readily than others. Knocking occurs when fuel burns unevenly in your engine's cylinders. When cylinders have the correct balance of air and fuel, fuel will burn in small regulated pockets instead of all at once, like sparklers, not like fireworks. After each pocket burns, it creates a little shock, igniting the next pocket and continue the cycle. Engine knocking happens when fuel burns unevenly and those shocks go off at the wrong time. The result? An annoying noise and potential damage to your engine's cylinder walls and piston. Experimental studies led to the determination that of the standard fuels available at the time, the most extreme knock was produced by a fuel composed of pure normal heptane, while the least knock was produced by pure isooctane. Isooctane is 2,2,4-trimethyl pentane. This discovery led to the development of the octane scale for defining gasoline or petrol's quality. If you use 2,2,4-trimethyl pentane as a fuel, it will create the least knocking. So the octane rating or octane number is 100 for this compound. The highly branched structure makes this compound to have less knocking. If you take pure N-heptane as a fuel, it will create maximum knocking due to its linear structure, and therefore the knocking rating or octane number is 0. Now consider a gasoline fuel sample with an octane number 85. It means that it will produce the same level of knocking that of a mixture containing 85% 2,2,4-trimethyl pentane and 15% N-heptane. Similarly, a petrol sample with a 78 octane number indicates that this fuel produces the same level of knocking that of a mixture containing 78% 2,2,4-trimethyl pentane and 22% N-heptane. One important thing to note: a sample petrol has an octane number 80 does not mean that the petrol contains 80% 2,2,4-trimethyl pentane and 20% N-heptane. It only means that the fuel produces the same level of knocking that of a mixture of 80% 2,2,4-trimethyl pentane and 20% N-heptane. Reforming is the process to get high quality, high octane number petrol from naphtha distillate and from lower quality of petrol. Now we will study about the chemistry in knocking. Wheeler et al. In 1948 found that knocking is connected with the production of peroxide in the last part of the fuel-air mixture to be burnt. In order to understand this mechanism, we will consider ethane as a fuel. Under the normal combustion, ethane will be converted into carbon dioxide and water. Equation is given. But during knocking, instead of this single reaction, improper combustion will take place and different series of reactions will occur compared to the normal combustion. For example, during knocking, first step will be the conversion of ethane to ethane peroxide. Second step will be the peroxide conversion to acetaldehyde. Third step will be the conversion of acetaldehyde to formaldehyde. And the last step will be formaldehyde into carbon dioxide and water. So these series of reactions will happen during the improper combustion at knocking. How to reduce knocking? We can use high octane gasoline, or we can get a low critical compression ratio, or anti-knocking agents such as tetraethyl lead, tetramethyl lead, methyl tertiary butyl ether, ethyl tertiary butyl ether, amyl alcohol, etc. Anti-knocking agent is a chemical substance added to petrol to improve the anti-knocking property of the petrol. For example, tetraethyl lead and tetramethyl lead, these two compounds were used in 90s, in 80s to reduce the knocking due to petrol. But now it is phased out. Now it is not being used because of the poisonous nature of lead. Nowadays, people use methyl tertiary butyl ether, ethyl tertiary butyl ether, tetramethyl alcohol as anti-knocking agent. So a small amount of this anti-knocking agent will be mixed with the petrol and will be used in petrol engines. Why we are not using lead-based anti-knocking? The reason one is the pollution, because it's a toxic metal. Second thing, in the catalytic converter that the vehicle has rhodium catalyst in it, that will be inactivated if lead is present in the exhaust gas. Next topic is cetane number. Cetane number or cetane rating is an indicator of the combustion speed of diesel fuel and the compression needed for ignition. It plays a similar role for diesel as octane rating does for gasoline. The cetane number is an important factor in determining the quality of the diesel fuel, but not the only one quality. Other measurements such as diesel's quality in terms of energy content, density, lubricity, cold flow properties, sulfur content, all these factors are also determine the quality of diesel fuel in addition to cetane number. Definition of cetane number. Cetane number is an inverse function of a fuel's ignition delay. Ignition delay is the time period between the start of the ignition and the first identifiable pressure increase during the combustion of the fuel. In a particular diesel engine, higher cetane fuel will have shorter ignition delay periods than lower cetane fuels. So, higher cetane number means it will take less time for the ignition. So, it will be having a shorter ignition delay. If a diesel is having lower cetane number means it will take a higher ignition delay or longer ignition delay period. Percentage of N-cetane present, the standard mixture of N-cetane and alpha-methyl naphthalene, which has the same ignition properties as that of the diesel under examination. I can tell this statement in a simple way. For example, generally diesel engine operates well within a cetane number of 48 to 50. For example, a sample of diesel fuel is having a cetane number of 48, which means it contains the ignition property of this diesel fuel will be equal to a mixture of 48% cetane and 52% alpha-methyl naphthalene. Now I think you understood the statement. Fuels with lower cetane number have longer ignition delays, requiring more time for the fuel combustion process to be completed. Hence, higher speed diesel engines operates more effectively with higher cetane number fuels. So in this video lecture, the following points were discussed: reforming process and its importance, knocking in engines and the reasons behind it, prevention or reduction of knocking, octane number and cetane number for fuels. Thank you for watching. Welcome to the video lecture on catalytic converter and biofuels. I am Dr. Jinish. I am from Department of Chemistry, Ramaya University of Applied Sciences. At the end of this video lecture, students will be able to describe the function of catalytic converters, explain the importance and sources of biodiesel and power alcohol, discuss the preparation of biodiesel and power alcohol. Car engines run on gasoline or diesel, which are made from petroleum. In theory, if you burn any kind of hydrocarbon fuel with oxygen from the air, you release a lot of energy and make nothing but carbon dioxide and water, which are clean and relatively harmless. In practice though, gasoline is a mixture of 150 different chemicals, not just hydrocarbons but additives too. And it doesn't burn as cleanly as we would like. That means you generally get some air pollution as a byproduct. The pollutant gases made by car engines include the poisonous gas called carbon monoxide, volatile organic compounds, nitrogen oxides that cause smoke, then the sort of choking, cloudy vehicle pollution we all know and hate. How to avoid these polluting gases in the exhausting gases from the release to the environment? The answer is the use of catalytic converters used in the vehicles. Device used to reduce the emission from an internal combustion engine used in most modern day automobiles and vehicles. Catalytic converters are used in exhaust systems to provide a site for the oxidation and reduction of toxic byproducts like nitrogen oxides, carbon monoxide and hydrocarbons of fuels into less hazardous substances such as carbon dioxide, water vapor and nitrogen gas. The diagram and the position of catalytic converter in the exhaust system of a car is shown in this figure. Catalytic converters were first widely introduced in American production of cars in 1975 due to EPA regulations on toxic emission reductions. The United States Clean Air Act required a 75% decrease in emission in all new model vehicles after 1975, a decrease to be carried out with the use of catalytic converters. Two main types of catalytic converters are available: honeycomb and ceramic beads type. This figure represents the working of a catalytic converter. Catalytic converter contains a zone for reduction which contains rhodium and platinum catalyst and an oxidation zone which contains platinum and palladium catalyst. When the toxic exhaust gases came from IC engine passes through catalytic converter and converted into non-toxic gas. The reactions are shown below. A reduction of nitrogen oxides into elemental nitrogen and oxygen. Second, oxidation of carbon monoxide to carbon dioxide. Third, oxidation of hydrocarbons into carbon dioxide and water. In these three reactions, we understood that there is a conversion from hazardous gases to less hazardous substances. There are few limitations for catalytic converters. Higher temperature is required for the functioning. It becomes damaged from road fragments. It becomes functionless after 80,000 kilometers. Also, unburned fuel damages the efficiency of catalytic converter. How we will be knowing that the catalytic converter is now defective? So these are the symptoms of defective catalytic converters: increase in fuel consumption of the vehicle, low response from engine even we accelerate, oxygen sensor alert, rattling noise due to soot deposition on the walls, engine stops frequently without a reason. So these are the symptoms of a defective catalytic converter. Now how can we extend the life of a catalytic converters? 1. Frequent maintenance of vehicle. 2nd, reinstallation of the catalyst in the converter after certain kilometers of usage of vehicle. Generally, the palladium catalyst to be replaced after 80,000 kilometers. Then use unleaded fuel in the vehicle. As the world human population grows and with changing consumer demands, sustained economic development will depend upon a secure supply of raw materials as inputs for manufacturing needs. The majority of consumer goods are currently made from hydrocarbons produced by petrochemical industry. Continued depletion of limited global natural resources supports the concept of supplying industrial production and energy needs through the use of renewable or bio-based resources. The wide variety of industrial products, including biomaterials, fuels, and biochemicals, are already manufactured from bio-based raw materials, which can be divided into 3 broad groups: biomaterials, energy fuels, and biochemicals. Biomass is an attractive energy source for a number of reasons. First, it is renewable as long as it is properly managed. It is also more evenly distributed over the Earth's surface than the other finite energy petroleum based resources, and may be exploited using more environmentally friendly technologies. Biomass provides the opportunity for increased local, regional, and national energy self-sufficiency across the globe. The energy in biomass can be assessed or accessed by turning the raw materials or feedstocks into useful form. Transportation fuels are made from biomass through biochemical or thermochemical processes. Known as biofuels, these include ethanol, methanol, biodiesel, biocrude, and methane. One of the major biofuel is biodiesel. Now we will study the preparation, characteristics, and advantages of biodiesel. Biodiesel is a general name for methyl esters from organic feedstock. So biodiesel, they are methyl esters. Biodiesel can be made from wide range of vegetable oils: jatropha plant extract, rapeseed oil, sunflower oil, palm oil, soybean based oil, recycled cooking oils. These oils can be used to prepare biodiesel. The raw material for biodiesel is mainly vegetable oil and animal fat. Biodiesel is made by converting these oils and fats into esterified oil by transesterification, and the reaction is given in the formula. Oil or fat, when it reacts with alcohol, it converts into glycerol and biodiesel. And biodiesel, we can see that they are methyl esters. The mechanism of this reaction is given here. The vegetable oil is a triglyceride, which is the ester of glycerol. The 3 ester part, which is shown in blue color in the vegetable oil, is reacting with 3 methyl group in the methanol, which is an alcohol, and form 3 methyl esters and glycerol as a byproduct. These 3 methyl esters are known as biodiesel. Generally, sodium hydroxide or potassium hydroxide are used as catalyst for this reaction. Now, the synthesis of biodiesel is shown in this figure. For the biodiesel preparation, mainly 3 chemicals are required. 1. Vegetable oil or fats. 2nd, methanol for transesterification reaction. 3rd, the catalyst, sodium hydroxide or potassium hydroxide. The pre-treated oil and fats will be mixed with the methanol and catalyst, and the reaction will continue for a stipulated time at an optimum temperature. After the transesterification reaction, the glycerin and biodiesel will be formed and the glycerin can be separated from the reaction mixture. Then the remaining biodiesel should be washed and dried. Biodiesel can be used pure or in blended form. Most common blend is 5% biodiesel and 95% diesel in vehicles. Blends above 30% may require modifications in the engine, because if you are using more biodiesel than the diesel amount, then it leads to rubber seals perishing and injectors blocking in the engine. So if you want to use pure biodiesel in vehicle, the engine of the vehicle should be modified for the use of biodiesel. Advantages of biodiesel. Biodiesel is biodegradable, so less harmful if it is spilled. It will degrade itself. It produces lower emission than the petroleum-based diesel. It is renewable energy resource, less hydrocarbon, carbon monoxide and particulates released by the combustion of biodiesel. Even though the emission of oxides of nitrogen is higher, but that we can deal with the use of catalytic converters in the vehicle. Use of 100% biodiesel would reduce life cycle carbon dioxide emission by 40 to 50%. So 40 to 50% carbon dioxide emission that we can achieve if we are using 100% biodiesel. Use of 5% blend, that is 5% biodiesel and 95% petroleum based diesel, will reduce the carbon dioxide emission by 2 to 2.5%, and biodiesel is eco-friendly. Disadvantages. Land requirement for getting vegetable oil from crops, because if you want to get the vegetable oil, then we have to cultivate that crops. For that we require land. Still emission will occur, and doesn't address the need to be more energy efficient. These are the disadvantages of biodiesel. Another biofuel is alcohol. Alcohols can be used as octane enhancers for petrol. By blending petrol with the absolute alcohol means 100% alcohol without any water content. So by blending petrol with absolute alcohol, we can make power alcohol and can be used in vehicles. Power alcohol is a mixture of 80% petrol, 20% ethanol and small amount of benzene. Oxygen present in the alcohol aids in complete combustion of the hydrocarbons in petrol, thereby reducing the peroxide formation, and hence knocking is reduced. We studied about knocking in my previous video lecture. Alcohol can be prepared from corns, molasses, etc. Now, advantages of power alcohol. Power alcohol has a better anti-knocking property, higher octane number. Alcohol blended petrol can be used in engines with a higher compression ratio. No starting difficulty with alcohol petrol blend in vehicles. Air required for complete combustion is less in power alcohol powered engines. Air required for complete combustion is less. Ethyl alcohol contains oxygen atoms, which helps for the complete combustion of power alcohol, thereby reduces carbon monoxide and volatile organic compound emissions, and economically cheaper. But there are some disadvantages of power alcohol. Alcohol lowers the calorific value of petrol, and difficulty in starting engine at lower temperature, that is a problem. At lower temperature you will face difficulty to start the engine of the vehicle. Ethyl alcohol may undergo oxidation reaction to form acetic acid, which corrodes the engine parts. That is a concern. Ethyl alcohol contains oxygen atom. The amount of air required for complete combustion is less, and therefore air regulation is required. Blending agents such as benzene or toluene are used, which is not good. And here there are few quiz questions you can answer yourself. Now we will summarize this video lecture. And we studied about the function of catalytic converters. They are devices used to reduce the emission from the internal combustion engine. Then we studied about biodiesel. They are biodegradable, less harmful if spilled, and produces lower emission than diesel renewable. And we studied about the preparation characteristics and advantages of biodiesel. Then we studied about power alcohol, which has better anti-knocking properties, higher octane number, and the alcohol blended petrol, that is power alcohol, can be used in engines with a higher compression ratio. Thank you for watching this video. Welcome to the new video lecture in a new topic, which is flue gas. My name is Dr. Jinesh. I am from Department of Chemistry, Ramaya University of Applied Sciences. Flue gases exit to the atmosphere via a flue. Flue means which is a pipe or a channel for conveying exhaust gases from a fireplace, oven, furnace, boiler, steam generators, other industries. You can see the pictures of those pipes which are known as flue, and the gases which are coming out from that pipes are known as flue gases. Quite often, the flue gas refers to the combustion exhaust gas produced at power plants, especially thermal power plants. So the gases, the combustion product or the exhaust gas which is coming out from the power plants, they are known as flue gas. Flue gas composition depends on what is being burned, but it will usually consist of mostly nitrogen. Typically more than 2/3 of the flue gases will be nitrogen, derived from the combustion of air, carbon dioxide, water vapor, as well as excess oxygen, which is also derived from the combustion of air. It further contains a small percentage or a number of pollutants such as particulate matter like soot, carbon monoxide, nitrogen oxides, and sulfur oxides. So the major components in flue gases are nitrogen, excess oxygen, carbon dioxide, soot, carbon monoxide, nitrogen oxides, and sulfur oxides. Most fossil fuels are combusted with ambient air. We don't use pure oxygen. We normally burn the fossil fuel in ambient air for generating power. Since ambient air contains about 79 volume percentage gaseous nitrogen, which is essentially non-combustible, the largest part of the flue gas from most fossil fuel combustion is uncombusted nitrogen. So why 2/3 is nitrogen? Because the ambient air that is used for the combustion of the fossil fuel is mainly contains nitrogen. So the non-combustible nitrogen will be the major part of the flue gas. Carbon dioxide, the next largest part of flue gas, can be as much as 10 to 25 volume percentage or more of the flue gas. Around 10 to 25% of the flue gas will be consisted of carbon dioxide. This is closely followed in volume by water vapor. Water vapor also similar amount of carbon dioxide. How water vapor is formed? Because of the combustion of hydrogen in the fuel. If the fuel contains hydrogen, definitely water vapor will be one of the combusted product. Much of the smoke seen pouring from the flue gas stacks is this water vapor forming a cloud as it contacts cool air. So you can see the white smoke comes out from the big towers or the flue pipes. They are mainly water vapor along with some soot. Much of a typical flue gas from the combustion of fossil fuel contains very small amount of nitrogen oxides, sulfur oxides, and particulate matter. The nitrogen oxides are derived from the nitrogen in the ambient air as well as from any nitrogen containing compound in the fossil fuel. So the nitrogen oxides, which is also present in the flue gas, it can be derived either from the nitrogen in the ambient air or if any nitrogen containing compounds present in the fuel. After burning, those nitrogen will be converted into nitrogen oxides. The sulfur oxide is derived from any sulfur containing compounds in the fuel. So if you burn a fuel which contains sulfur, then that sulfur will be converted into sulfur oxides during the combustion or burning of the fuel. The particulate matter is composed of very small particles of solid materials and very small liquid droplets which give flue gases their smoky appearances. So the particulate matter is one of the reasons behind the smoky appearance of the flue gas. The steam generators in large power plants and the process furnaces in large refineries, petrochemical, chemical plants and incinerators burn considerable amount of fossil fuels and therefore emit large amounts of flue gas to the ambient atmosphere. One of the effects of flue gases in the atmosphere is acid rain. Acid rain results when sulfur oxides and nitrogen oxides are emitted into the atmosphere and transported by wind and air currents. The sulfur oxides and nitrogen oxides react with water, oxygen and other chemicals to form sulfuric acid and nitric acid. Then these acids mix with water and the other materials before falling to the ground, especially during the time of rain. While a small portion of the sulfur dioxide and oxides of nitrogen that cause acid rain is from natural sources such as volcanoes, but most of the time the acid rain is due to the burning of the fossil fuels. The major sources of oxides of sulfur and oxides of nitrogen in the atmosphere which cause acid rains are the burning of fossil fuel to generate electricity, 2/3 of sulfur dioxide and 1/4 of oxides of nitrogen in the atmosphere come from electric power generators. Then these again sulfur dioxide and oxides of nitrogen, they are being produced from vehicles and heavy equipments and also from manufacturing industries, oil refineries and other industries. So after the production of sulfur dioxide and oxides of nitrogen from these industries, the winds can blow these sulfur dioxide and oxides of nitrogen over long distances and can cross borders, making acid rain a problem for everyone and not just those people who live into those close to those sources. So if you imagine that acid rain will happen only in the places where so many industries are there, you are actually wrong. Those oxides of nitrogen and sulfur can be carried away by winds and the acid rain may even occur in the nearby places of those industrial area. Here I'm showing you one acid rain pathway, one figure. This image illustrates the pathway for acid rain in our environment. Emissions of sulfur dioxide and nitrogen oxides are released into the air, where the pollutants are transformed into acid particles and may be transported long distances by wind. These acid particles then fall to the earth as wet and dry deposition during rainfall, snowfall, even through dust, and may cause harmful effects on soil, forest, streams and lakes, and it can damage the agricultural farmlands in a serious way. Here I'm showing you one picture. This is a sandstone statue built in 1702. These are the two photographs taken at different times. The left side, the sandstone photo was taken in 1908 and the right one in 1969. Then you can see that sandstone is almost destroyed, and this reason for the destruction was the acid rain which happened quite often in those areas. We will concentrate sulfur dioxide as a flue gas in the coming few minutes. Fossil fuels such as coal and oil contain a significant amount of sulfur. Fossil fuel, when burned, about 95% of the sulfur is converted into sulfur dioxide. High gas temperature of 800 degrees Celsius, which will favor the formation of sulfur dioxide to sulfur trioxide, because the fuel may contain some metals which can act as a catalyst for this reaction. So at high temperature and in the presence of metals in the fuel, the sulfur dioxide will be further oxidized to form sulfur trioxide. And in whatever way sulfur trioxide is formed, it does not behave like sulfur dioxide. Sulfur trioxide forms liquid aerosol known as sulfuric acid mist that is very difficult to remove. Sulfuric acid mist is often caused the blue haze that often appear as flue gas plume dissipates. This problem is being addressed by the use of wet electrostatic precipitators that we will study later. Then how we can avoid or limit the sulfur dioxide emissions? The principal approaches to controlling sulfur dioxide or sulfur trioxide emissions including use of low sulfur fuel. So if you use fuel which contains very low amount of sulfur, then the amount of sulfur dioxide produced after the combustion will be less. Or reduction or removal of sulfur in the feed, use of appropriate combustion technology. Or if you are getting a fuel which contains sulfur dioxide or which contains sulfur, then what you do before doing the combustion, you remove that sulfur from the fuel. Right? That is also one of the approach. Or after the combustion, if sulfur dioxide or sulfur trioxide is formed, don't allow those gases to escape to the atmosphere. Treat them properly. And one of the technique to treat the flue gases exhaust is known as flue gas desulfurization technique. We will study about flue gas desulfurization technique in detail. Since sulfur emissions are proportional to the sulfur content of the fuel, an effective means of reducing sulfur trioxide emissions is to burn low sulfur fuels such as natural gas, low sulfur oil, or low sulfur coal. Natural gas has the added advantages of emitting no particulate matter when burned, but every time we cannot use these fuels to reduce the amount of sulfur dioxide discharge. Sulfur in oil can be removed through chemical desulfurization process. So before the combustion, you can take the fuel and remove sulfur from that fuel using chemical desulfurization method. But this is not widely used in commercial technology outside the petroleum industry. Petroleum industry does this work very efficiently. They try to remove sulfur from the petroleum before using that petroleum products for further applications. Flue gas desulfurization is the process of removal of sulfur containing compounds from the flue gas coming out from industries. It may be carried out using either of two basic flue gas desulfurization system, regenerable and throwaway. So regenerable means you will be able to recover the sulfur and can be used for other purposes, or you can just remove the sulfur containing compounds from the flue gases. Both methods may include wet or dry process, depends on whether the process needs water or not. Currently, more than 90% of utility flue gas desulfurization systems use a wet throwaway system process, because throwaway systems are inexpensive scrubbing mediums that are cheaper to replace than to regenerate. So regenerating techniques are much costlier, but throwaway wet scrubbing systems are easier to perform and they are cheaper methods. Regenerable systems use expensive adsorbents or sorbents that are recovered by stripping sulfur oxides from the scrubbing medium. We will study in detail about these techniques later. These produce useful byproducts including sulfur, sulfuric acid and gypsum. For example, if you can remove the sulfur and sulfuric acid from the flue gas and can utilize it, right, then you can get some money out of the flue gases. Regenerable flue gas desulfurization generally have higher capital cost than throwaway systems, but lower waste disposal requirement and cost. So throwaway systems are cheap, but you will not be able to get money out of it. But if you can invest huge amount of money and install a regenerating flue gas desulfurization technique, even though the initial cost will be higher and the sorbents that you are using is also costlier, but you will be able to recover the sulfur oxides and can be utilized for making sulfuric acid and other products. Flue gas desulfurization techniques can be categorized like in this chart, and we will study each techniques in detail. Flue gas desulfurization processes. The major flue gas desulfurization processes are limestone scrubbing, lime scrubbing, dual alkali processes, lime sprays drying, Wellman load process. First we will study about limestone scrubbing. It is a once-through process. Limestone slurry is sprayed on the incoming flue gas. So the sulfur dioxide in the flue gas gets absorbed, and the reaction of removing sulfur dioxide is given as the limestone calcium carbonate, which will absorb the sulfur dioxide and form calcium sulfite. This calcium sulfite can be used to prepare gypsum. Second technique is lime scrubbing. Lime scrubbing is a wet once-through process. Here, lime, which is calcium oxide, will be mixed with water, form calcium hydroxide. Then this calcium hydroxide, which can react with the sulfur dioxide in the flue gas and form calcium sulfide. So the equation calcium hydroxide plus sulfur dioxide gives calcium sulfite. This calcium sulfite can also be used to prepare gypsum. Now, what are the major disadvantages of these two methods, limestone scrubbing and lime scrubbing? Lime and limestone scrubbing lead to deposits inside at the tower. That means the final product is calcium sulfite. So this calcium sulfite deposit may block the nozzles through which the scrubbing slurry is sprayed. So normally this limestone and lime scrubbing, we are spraying a slurry. That nozzle will be blocked because of the deposits of the product calcium sulfite. Compared to limestone scrubbing, lime scrubbing is expensive because the cost of calcium oxide is much higher than that of calcium carbonate. Third technique is dual alkali system. Dual alkali system uses two reagents, sodium sulfite and sodium hydroxide, inside the spray chamber to remove the sulfur dioxide. Resulting products will be sodium salts. They are sodium sulfite, sodium sulfate ions are precipitated, and we can regenerate sodium hydroxide. So here one of the reactant that we put to remove sulfur dioxide, that is sodium hydroxide, we will get it back. But whatever sodium sulfite that we are supplying, that we will not get it back. The system has zero liquid discharge and eliminate the need for wastewater discharge permit. So this process actually will not produce any wastewater as the byproduct. So this system has zero liquid discharge and we don't require any wastewater treatment plant. Fourth technique is lime spray drying. Here it is a dry process. Unlike the lime scrubbing and limestone scrubbing, this is a dry process. Lime slurry is sprayed into the chamber. Then sulfur dioxide in the flue gas is absorbed by the slurry. But here the liquid to gas ratio is maintained such that the spray dries before it reaches the bottom of the chamber. So from the top, if you supply the lime slurry means through a nozzle. So here the liquid to gas ratio is maintained such that the spray dries before it reaches the bottom of the chamber. That means after the absorption of sulfur dioxide, the lime slurry will come down at the bottom of the chamber, but when it reaches the bottom of the chamber, the water content will not be there. So the final product that we will get at the bottom of the chamber will be a solid product. These dry solids are carried out with the gases and are collected in fabrication unit. System needs lower maintenance, lower capital cost and lower energy usage. So the final product that we get, that means sulfur dioxide absorbed in the lime slurry, that we have to filter using a fabric filtration unit because it is a powder kind of material. Fifth process is Wellman load process. The Wellman load process is a regenerable process. All other processes were once through process. Here it is a regenerable process. That means we can get that sulfur dioxide back after removing from flue gases and can be used for some other purposes. The Wellman load process is a regenerable process to remove sulfur dioxide from flue gas. That process is a flue gas desulfurization process without creating a throwaway sludge product. So it will not create any product like gypsum or calcium sulfide. Rather, we will be able to recollect the sulfur dioxide and the reagent can be reused again. In this process, sulfur dioxide from flue gas is absorbed in a sodium sulfite solution in water, forming sodium bisulfite. Other components of flue gases are not absorbed, only sulfur dioxide will be absorbed by sodium sulfite, and the reaction is sodium sulfite reacts with the sulfur dioxide and water, forms sodium bisulfite. Then we have to reduce the temperature of this mixture. So this sodium bisulfite will be converted into sodium pyrosulfite, which will be precipitated. So here you see the equation. The sodium bisulfite will be converted into sodium pyrosulfite at low temperature and it will be precipitated. Now get that precipitate, then upon heating, the two previously described chemical reactions are reversed and sodium pyrosulfite is converted to a concentrated stream of sulfur dioxide and sodium sulfite. So here you can see sodium pyrosulfite will be decomposed to sodium bisulfite, then again that sodium bisulfite will be decomposed and you will get the sulfur dioxide back. So from the flue gas you will be able to separate the sulfur dioxide. This sulfur dioxide can be used for further reaction, that is for the production of sulfuric acid. Sulfur dioxide is the major reactant for producing sulfuric acid. And sulfite, sodium sulfite, you will get it back. So again you can use the sodium sulfite for the Wellman load process. So you will not be losing any reactants for removing the sulfur dioxide from the flue gas process.